Welcome to the third class for the amateur radio license technician level. This is going to be chapter 3. We're going to talk about electricity. My name is Richard Montel, call me Rick, and my call sign is Kilo Whiskey 4, Mike, Quebec. So, you want to give me the next slide. Radios are powered by electricity, and radio signals are a form of electrical energy. A basic understanding of how we control electricity allows you to better install and operate your radio. Electrical charges can be positive or negative. Opposite charges attract each other, and like charges repel. Electrical current is the flow of electrons. Electrons are negatively charged atomic particles, usually surrounding an atom's positively charged nucleus of protons, which are positive, and neutrons, which are neutral. They don't have a charge at all. Electrons move in response to an electromotive force and can move independently of the atoms. Okay, basic electrical concepts. Current. The movement of electrons measured in amps with an ohm meter, or amp meter, I'm sorry, measured in amps with an amp meter and represented by I, the capital letter I, in formulas. Voltage. The amount of electromotive force, abbreviated as EMF, also called electrical potential. We measure it in volts with a voltmeter, and it's represented by the capital letter E or the capital letter V in the formulas. Resistance is the opposition to the movement of electrons. It's measured in ohms by an ohm meter and represented by the capital letter R, or sometimes the omega sign in scientific publications and formulas. Resistance is like friction, and it turns electrical energy into heat when current flows. Conductors permit current to flow, low resistance, and insulators block current flow, considered high resistance. The flow of water through a pipe is a good analogy to understand the three characteristics of electricity and how they are related. Okay, diagram on the left, you have a pump, got a pressure gauge showing you how much pressure the pump is putting out. The current, or water, is carried inside the pipe or tubing. You have a flow meter, which measures how much water is passing past that point in a given time. On the right side, we have an equivalent electrical circuit. You have a battery, which is a source of EMF, electromotive force. We have a voltmeter, which is the equivalent of a pressure gauge. It measures how much force is in the electrical circuit, or voltage. And then you have a current meter, amp meter, measuring the electron flow through the wire going past that point in the wire. And we would read that out in amps or milliamps or some level of amperage. Next. Polarity refers to the convention that determines which voltages are positive and negative. Voltage from a source of electrical energy causes current to flow. Resistance is the material's opposition to the flow of current. Voltage, current, and resistance affect each other. They're all tied together. For example, higher voltage, bigger push, more pressure, however you want to refer to it, but the proper electrical term is higher voltage, causes more current to flow if the resistance stays the same. Okay? Do some practice questions. Electrical current is measured in which of the following units? We measure current in amps. D. What is the name for the flow of electrons in an electric circuit? And when electrons flow, that's a current. D. What is the electrical term for the force that causes electron flow? That would be A, voltage. That's the pressure, the electrical force that moves the electrons, makes them flow. Next. Which of the following describes alternating current? C. Current that alternates between the positive and negative directions. It has to reverse direction to be alternating current. Which instrument would you use to measure electric potential? B. A voltmeter. Electric potential is like electrical pressure. We measure that with volts. Which instrument is used to measure electric current? D. An ammeter. Two kinds of current. We have current that flows in only one direction is called direct current. Batteries are a common source of DC. Current that flows in one direction, then in the opposite direction is called alternating current. Household current is AC. AC current reverses direction on a regular basis. Each process of reversing is a cycle. The number of cycles per second is frequency, and we measure that in hertz. And 1 hertz is equal to 1 cycle per second. And if you look at the diagram on the right, oh, it's gone. If you look at the diagram on the right, the upper one is DC, varying DC, and the lower one is AC. And if you notice in AC, the current goes negative below zero. The line that has the word time on it is the zero line. So the upper one, DC, you can have it flowing, decreasing, stopping, but it doesn't reverse. It's flowing again. That's, in that particular case, that's pulsating DC. The lower one, it actually reverses. That makes it AC. All right. Next slide. Current flow. A circuit is any path through which current can flow. Electrical circuits are made from components and the connections between them. If two or more components are connected in a circuit so that the same current must flow through all of them, that is a series circuit. A short circuit is a direct connection between 2 points in a circuit. And I'm going to expand on that a little bit and say a short circuit is an unintentional direct connection, because if it was an intentional connection, like running a wire from A to B, that's not what we would call a short circuit. That's just a connection. But when you have a short circuit, that's an unintended connection. Okay, an open circuit is made by breaking a current path in a circuit. So you have a connection that opens up, you have a wire that breaks, switch that opens, that causes an open circuit. All right, next. Series circuit. Here we see a simple circuit. You have a battery, you have 3 light bulbs, R1, R2, and R3. We're calling them R because each light bulb is a resistance. And any current that flows into bulb number 1 is also going to flow into bulb number 2. You have no other route available. Each bulb gets, any electron that goes into R1 is going to go into R3. So the same current at all points in the circuit. That's an important thing to keep in mind. The current is the same all the way around the circuit. Series circuits provide one and only one path for current flow. Okay? Here's a parallel circuit. We have a battery again. We have 3 light bulbs, resistances 1, 2, and 3. But in this example, which is a parallel circuit, the electrons could flow different routes. Electrons that go through resistance 1 or bulb 1 are not going to go through resistance 3. So you could have more current flowing in R1 or R2 than what you have in R3 or vice versa. But the voltage is the same. All of the connections are across the top are connected on the positive side of the battery. The ones on the lower part of the circuit are all connected to the negative terminal of the battery. There's an equal voltage across each bulb. The current might be different, but the voltage is the same. Parallel circuits provide multiple paths for current flow. Next. Which type of circuit is DC current the same through all components? Okay, the current is the same in a series circuit. In what type of circuit is voltage the same? Voltage the same across all components. The voltage is the same in a parallel circuit. How is a voltmeter connected to a component to measure the applied voltage? We connect voltmeters in parallel. When configured to measure current, how is a multimeter connected to a component? When we're measuring current, we connect the meter in series. When configured to measure current, how is a multimeter connected in a component? That's in series. The basic electrical test instruments are simple meters, voltmeters, amp meters, and ohm meters. So that a separate meter isn't needed for each parameter, the multimeter was invented. That's short for a multifunction meter. Measures all 3 electrical values of voltage, current, and resistance. Doesn't do them all 3 at the same time, but it has the ability to measure all 3 parameters. Other names, volt ohm meter or dBm, which is a digital voltmeter. Ways that meters are damaged. Dropping them on the floor. Okay, measuring voltage of an energized circuit when the meter is set to measure resistance. When you have an ohm meter or voltmeter or a MOV set up for measuring ohms or resistance, there's a battery in the meter that provides a current through the circuit. It's a very, very small current. The meter is not set up to measure voltage or current. And if there is power on the circuit, it can enter the leads on the meter and damage the meter. Another way of damaging a meter is exceeding the meter's voltage rating. Voltmeter and leads are, in this case, not rated for the voltages to be measured. You exceed those ratings, and you can get shocked. You can short out the leads. You can ruin the voltmeter. So you want to make sure that the leads and the voltmeter are rated for the voltages you're going to be checking. Practice questions. Which of the following can damage a multimeter? C. Attempting to measure voltage when using the resistance setting. You want to make sure when you're in the resistance mode, you do not use a live circuit. Okay, which of the following measurements are made using a multimeter? The answer is C, voltage and resistance. What reading indicates that an ohm meter is connected across a large discharged capacitor? Well, I need to talk about what a capacitor is. Capacitor is like a small battery. And if remember I said that the ohm meter provides a voltage on the circuit. That comes from the meter itself. That's why you have to have the circuit unpowered. So what happens when you hook this ohm meter up is that the initial indication is a low resistance because current will flow into the capacitor and charge it. And then as the capacitor gets charged, the amount of current would decrease, which is an indication of an increase in resistance. So the correct answer is A, increasing resistance with time. Which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter? And the correct answer is B, ensure that the circuit is not powered. Unplug the device. Which of the following precautions should be taken when measuring high voltages with a voltmeter? Answer is B, and it is important. Ensure that the voltmeter and the leads are rated for use at the voltages to be measured. And the owner's manual for the meter will tell you what those ratings are and check it. All right, we're going to talk about Ohm's law. E represents voltage units, volts. I represents current. We measure that in amps. R represents resistance. We measure that in ohms. The relationship between current, voltage, and resistance can be seen as three different formulas that are all related. R equals E divided by I is equal to E divided by R, and E is equal to I times R. On the top right, we have a circle that has those three letters. If you wish to find one of those items, cover it up, and the formula is presented by the remaining letters. In other words, if I wanted to find R, I would cover R. The formula would be E divided by I. If I wanted to find I, cover it up, and you have E divided by R. If you want to find the voltage, E, you cover it up, and the formula is I times R. Okay? Examples on how to use Ohm's law. All right, so we have another circuit, simple series circuit, battery. Voltage is unknown. We're going to want to find the voltage, E. The resistance is 10 ohms, and the current is 2 amps. If you use the circle and you cover the E, then the formula would be I times R, or 2 times 10 should be 20 volts. Okay, another simple series circuit. This time we know the battery voltage, it's 12 volts. We know the resistance is 6 ohms. We don't know what the current is. So if we cover the I in the circle, the formula would be E divided by R, which would be 12 divided by 6 is 2 amps. Next. Okay, now we're going to do them without the drawings. I'm just going to use the math. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So we want to find R. So if we cover the R, we're going to have 90 volts divided by 3 amps. It's going to give us 30 ohms. What is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? Again, if you use the circle, we want to find the current. So it's going to be E, which is 120 divided by 80, which is 1.5. What is the voltage across a 2 ohm resistor if a current of 1/2 amp flows through it? So we know R and we know I. The formula it would be I times R. 2 times 1/2 would be 1 volt. Okay, practice questions. What are the units of electrical resistance? Ohms. We always talk about ohms when we're talking about resistance. Why are metals generally good conductors of electricity? Correct answer is B. They have many free electrons. Which of the following is a good electrical insulator? The correct answer is B, glass. What formula is used to calculate the current in a circuit? So if you go back to your circle again, I, the current, is equal to E divided by R. The correct answer is B. What formula is used to calculate voltage in a circuit? And E is equal to I times R. A. What formula is used to calculate resistance in a circuit? And we know that R is equal to E divided by I. What is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So 90 divided by 3 is going to give you 30 ohms. Answer B. What is the resistance of a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? So 12 divided by 1.5 is going to be equal to C, 8 ohms. What is the resistance of a circuit that draws 4 amps from a 12 volt source? So 12 divided by 4 is going to be 3 ohms. Answer A. What is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? So we're going to have 120 divided by 80. That's going to be 1.5 amps. Answer D. What is the current through a 100 ohm resistor connected across 200 volts? 200 divided by 100 is going to be 2 amps. Answer C. What is the current through a 24 ohm resistor?
Oops.
Okay, try this again. What is the current through a 24 ohm resistor connected across 240 volts? So voltage 240 divided by resistance 24 is going to give you 10 amps. Correct answer is C. What is the voltage across a 2 ohm resistor if a current of 1/2 amp flows through it? So we're going to have 0.5 times 2 ohms, and that would give us 1 volt. Answer A. What is the voltage across a 10 ohm resistor if a current of 1 amp flows through it? So the correct answer would be 10 volts. Answer B. Next. Okay, what is the voltage across a 10 ohm resistor if a current of 2 amps flows through it? So voltage is equal to I times R. 10 times 2 would be 20 volts. Answer D. Okay, we have a similar formula for power. Use the same circle, P, power, represented by the letter or the symbol P is the rate at which electrical energy is used. We measure it in watts, W. A device that consumes or dissipates power is referred to as a load. Okay, and the formulas are very similar. Power is equal to I times E. E, or the voltage, is equal to power divided by I. And the current is equal to the power divided by E. Okay, so use a circle the same way in using power, calculating power, as you would with the Ohm's law. All right, next. How much power is delivered by a volt?
Excuse me.
We've got to back up. Okay, electrical power is measured in which of the following units? Power is watts. B. Which term describes the rate at which electrical energy is used? Correct answer is C, power. What is the formula used to calculate electrical power in a DC circuit? And power is equal to I times E, the current times the voltage. How much power is delivered by a voltage of 13.8 volts and a current of 10 amps? So we multiply the voltage by the current and we get 138 watts. How much power is delivered by a voltage of 12 volts DC and a current of 2.5 amps? So voltage times current, 12 times 2.5 is 30 watts. B. How much current is required to deliver 120 watts at a voltage of 12 volts DC? You would have to have 10 amps to get 120 watts, and that would be answer B, 10 amps. Okay, components and units. Components in electrical circuits perform functions such as storing or using energy, routing current, or amplifying circuits. amplifying signals. The three most basic types of electronic components are resistors, capacitors, and inductors. We could use actual drawings to show how components are arranged in circuits, but this would be too cumbersome for most circuitry. Instead, we use schematic diagrams. And if you look at the diagram here on the right, it does show you what components make up the circuit. It does not necessarily show you their physical location relative to each other. It does show you how they are electrically connected. And if you follow the wires, item 2, fuse 1, is wired directly to switch 1, item number 3, but they may not be that close together in the box. So it's an electrical relationship, not a physical one. Okay? Resistors. The function of a resistor is to restrict the flow of current just as a valve in a water pipe restricts the flow through the pipe. We measure resistance in ohms, and we use the symbol omega or the word ohms. Remember Ohm's law. And they give you the three variations of Ohm's law down below. I equals I times R. I equals E divided by R. E equals I times R. And R equals E divided by I. Okay? The symbol for resistance on electrical schematic is the jagged line. You see one at the top of the box on the right. And then second symbol down, the potentiometer, or we call them pots. That's a variable resistor. And when you see an arrow, that means it's adjustable. So in this case, we're talking about an adjustable resistance. And a common use for that would be like on a volume control. Next. Resistors. Okay. We see a picture of a resistor. Resistors have a color code, which helps us identify the resistance value of that resistor. And it will tell you what the actual resistance is supposed to be, and then the last band, in this case the silver band, would also tell you the tolerance on that resistance. In other words, 5% accuracy, 10% accuracy, etc. Okay, we've got a large variety of resistors in this picture. The large one at the top appears to be a wire wound resistor. They actually just take wire, wrap it around the form, and as a given length of wire has a given resistance, longer wire would have more resistance. The third one down in the center, if you see the metal band on it, is also wire wound, but that metal band is electric. It can connect to the wire that is wrapped around the form, and that's a variable resistance. You can slide that metal tab left and right, and that will change the length of wire that is in the circuit. And then there's a few other examples of resistors there as well. Next. Capacitors. The function of a capacitor is to store electrical energy called capacitance. We see a schematic symbol on the right. They show you the two electrodes of the capacitor. There is a gap between. The gap has the dielectric material, the insulator. And the second symbol down has an arrow through it, which means that is a adjustable capacitor. You can think of capacitors as being like very small batteries. They store energy in an electrical field, and that's an important thing to remember. It's an electric field that is created by voltage between the electrodes with insulating dielectric material between them. There's different kinds of dielectrics. There's mica, there's glass, there's air. Sometimes we just separate the plates physically, and the air gap is the dielectric. And different kinds of dielectric have different values that they add to the amount of capacitance, different efficiencies, so that some physically same size capacitors will have different capacitance based on the dielectric material that is used. Okay. Here we have a picture of a small capacitor. Now, something you want to keep in mind with capacitors, we rate them two ways: the amount of capacitance that they hold and the voltage that they can withstand. Like on this one right here, the lower line of lettering there says 1 kV. That means that capacitor is rated for 1 kilovolt, 1000 volts. If you put a higher voltage than that on that capacitor, it will likely short out across the dielectric between the two plates and ruin the capacitor. Okay. But keep in mind, you store electrical energy in an electric field. It's created by the voltage between two conducting surfaces or electrodes. So think of it as like two conducting plates, something separating them. The electrodes are separated by an insulator, or in the case of capacitors, refer to it as a dielectric, because different kinds of dielectric, different materials, will have different efficiency on the capacitor. Storing energy this way is called capacitance, and we measure it in farads. There's a large variety of capacitors. And if you notice the larger one kind of in the center of the picture there, the labeling tells us it's rated for 470 microfarads. The farad itself is a very large quantity of capacitance. And so most of our stuff that we deal with in capacitors is microfarads, which is a millionth of a farad. Millifarads are uncommon, but that would be 1,000th of a farad. We do go to picofarads, which is a billionth. And so generally speaking, we're going to be dealing in some small portion of a farad when we're talking about the value of a capacitor. So this one's 470 microfarads, and its maximum voltage rating is 50 volts. If you put something higher than that, it's going to short across, ruin the capacitor. Next. Talk about inductors. The function of an inductor is to store energy in the magnetic field. We create that magnetic field by current flowing in a wire. When electrons flow in a wire, they create a magnetic field. This energy we call inductance, and it's measured in henries. And henries are also a very large value of inductance, so we tend to deal with millihenries and microhenries. All right, made from wire wound in a coil, sometimes around a core of magnetic material that concentrates the magnetic energy. And here is the symbol you see on the schematic. If you notice, this one is rounded. It kind of imitates the coils, one wrapped behind the other. It's different from a resistance symbol because the resistance symbol is pointy, top and bottom. This one is curved. And in the second one down, you see the arrow, which tells you that would be an adjustable inductance. In the photographs below, we see two different kinds or styles of inductors. The one on the bottom left is a wire wound over an air coil. It's just a piece of wire. Take a pencil, wrap the wire around the pencil, and there you have a small inductor. Take the pencil out, it's ready to solder on. The picture on the right, we have an inductor which is wound around a magnetic coil. It looks like a donut. That donut device is made out of some form of magnetic material. It can be ferrite. That's one of the more common ones. It can be powdered iron. There's variations. They do that because it increases the efficiency of the inductor. It gives you a larger value of inductance for a given amount of wire. Okay, next. Variable components. All three types of basic components are also available as adjustable or variable models. And we showed the schematic symbols for them. And what you see here are variable resistors called potentiometers or pots. Variable resistor is also called a potentiometer, frequently used to adjust voltage or potential, such as for a volume control. Okay, transformers. Transformers are made from two or more inductors that share their stored energy. Allow energy to be transferred from one inductor to another while changing the combination of voltage and current. As an example, a transformer is used to transfer energy from household 120 volt AC voltage to a lower voltage for other uses, such as in electronic equipment. In a common use for years on a transformer was to have a small transformer installed usually in the attic or in a closet out of the way that transferred the 120 volts in your house to 24 volts, which would operate the doorbell. That gave you a safe voltage at the button on your door in case it was raining out or something. You didn't want your guests to get zapped when they pushed the button. So we use a transformer to drop that voltage to a safe voltage. So we see the symbol for a transformer in the top right. It's two windings of an inductor, and we put the bars between them to indicate that they are the inductance from one is tied in with the inductance of the other. They interact with each other electronically. Below you see a photograph of a transformer. Okay. All right. What describes the ability to store electricity in an electric field? In an electric field, it's capacitance. Answer D. What is the unit of capacitance? A, the farad. What describes the ability to store energy in a magnetic field? That would be D, inductance. What is the unit of inductance? Answer is C, the Henry. What electrical component opposes the flow of current in a DC circuit? And the answer to that would be a resistor, B. What type of component is often used as an adjustable volume control? The answer is C, a potentiometer. What electrical parameter is controlled by a potentiometer? Resistance, B. It's an adjustable resistor. Okay, what electrical component stores energy in an electric field? That would be B, a capacitor. What type of electrical component consists of conductive surfaces separated by an insulator? That would be a capacitor, D. What type of electrical component stores energy in a magnetic field? That would be an inductor. If it's a magnetic field, it's an inductor. Answer C. What electrical component is typically constructed as a coil of wire? D, an inductor. What component changes 120-volt AC power to a lower AC voltage for other uses? That would be B, a transformer. Okay, reactance and impedance. In a resistor, AC voltages and currents are exactly in step, or they're in phase with each other. In capacitors and inductors, voltage and current have a phase difference. Capacitors and inductors store energy rather than dissipating it like resistors. Energy storage creates an effect called reactance. The symbol for reactance is a capital X. That acts like a resistance in opposing the flow of AC current. Capacitors create capacitive reactance, XC. Inductors create inductive reactance, XL, and the effects are complementary with each other. And you only have reactance in an AC circuit. The combination of resistance and reactance, in other words, measuring them both together, is called impedance, and that is represented by the symbol Z. Impedance represents a circuit's opposition to both the AC and DC current. Radio circuits almost always have both resistance and reactance, so impedance is often used as a general term to mean the circuit's opposition to AC current flow. What is the unit of impedance? That would be D, the ohm. What is impedance? A, the opposition to AC current flow. You can think of it as like AC resistance, but it only applies to the AC portion of the circuit. All right, resonance. Circuits that contain both a capacitor and an inductor are called resonant circuits or tuned circuits. A component's reactance depends on the frequency. This is important to remember. XL, which is inductive reactance, increases with frequency. As the frequency goes up, the resistance increases on an inductor. While the XC, or capacitive reactance, decreases. So as the frequency goes up, the AC resistance, or the reactance of the XC decreases. So higher frequency, the reactance on capacitor, the resistance of a capacitor goes down, and the resistance of an inductor goes up. Okay? At the frequency for which a circuit's XL, that would be the inductive reactance, and XC, that's the capacitive reactance, are equal. Remember, they're changing with frequency. So when you find the frequency where they're equal, their effects cancel. And this is the circuit's resonant frequency. At resonance, a circuit has only resistance. There's no reactance. It's strictly resistance, the DC part. And that affects the AC and DC current equally. A tuned circuit acts as a filter, passing or rejecting signals at its resonant frequency. And whether it passes them or rejects them has to do with how the two components are connected to each other. And you can select by design whether it passes a given frequency or rejects a given frequency. Okay? Here's a resonant or tuned circuit. Capacitors and inductors connected together create a tuned circuit. We have an inductor and a capacitor. They are connected to each other, and they affect each other at the resonant frequency. They zero each other out. Okay? When the XL, that is the inductive reactance, and the XC, that's the capacitive reactance. Remember, they change with frequency, so at a given frequency, they're going to be equal to each other. One's going up with frequency, the other one's going down with frequency, but there's a frequency where they're equal. That's the resonant frequency. The circuit is resonant at that point. Go back with one little bit. Let me get that last part. If C or L are adjustable, the capacitance or the inductance are adjustable, the resonant frequency can be varied or tuned. So you can make an adjustable resonance if one of those components, or even if both of those components are adjustable, but only one actually needs to be. Okay, next. Practice questions. Which of the following is combined with an inductor to make a resonant circuit? You need two things, a capacitor and an inductor. So the correct answer is D, capacitor. Which of the following is a resonant or tuned circuit? And the answer is A, an inductor and a capacitor in series or parallel. All right, diodes, transistors, integrated circuits. And early on, we talked about insulators such as glass, wood, talked about conductors, different metals, aluminum, copper. We said that was the two choices. Well, there's actually a third choice. We call them semiconductors. They're not really conductors. They're not really insulators. Silicone happens to be a material that fits into that class. They're okay inductors, but they're not as good as the metals are. Okay? Impurities are added to semiconductors to create materials with more than the usual number of electrons. Those are N-type. or fewer than the usual electrons, and that would be the p-type. Structures of N and P material can control current flow through the semiconductor. So you can have N-type and P-type. When N and P-type material are placed in contact with each other, the result is a p-n junction that conducts better in one direction than the other. And it's a drastic difference, typically. Okay, diodes. Diodes allow current to flow in only one direction, so like a check valve. They consist of two electrodes, an anode and a cathode. AC current is changed to varying pulses of DC. That's called rectification, the process of taking AC and converting it to pulsating DC is called rectification. Diodes used to change AC power to DC power are called rectifiers. And basically what they are is heavy-duty diodes. Okay, we've got a schematic representation here. The symbol is an arrow pointing at a bar. And the current flows in the direction the arrow points. So it goes from the arrow towards the bar. The anode is the positive side. The cathode is the negative side when current is flowing. There are variations in the symbol to represent different kinds of diodes, different variations of diodes. The one at the very bottom has the little arrows coming off of it, and that tells you that it is a light emitting diode. An LED, those are photons. They represent photons coming off of the diode. And in the very bottom of that box, it shows you a diode. There is a band or a bar at one end of the diode that is representative of the bar in the schematic, so you know which end is the anode and which end is the cathode. The current flows towards the bar. Okay, designator, when you see it in a schematic circuit, typically would be a capital D, like D1 or D2, as you list the different diodes in the circuit. Or CR is sometimes used, but that's going out of favor over time. All right, next. If AC voltage is applied to a diode, the result is a pulsating DC current because current is blocked when the voltage tries to push the electrons in the wrong direction. So it'll flow from A to C, but it will not flow when the current or the voltage in the circuit reverses for the reverse portion of the AC. It has to have a reverse portion to the AC. It cannot flow from the cathode to the anode, so it only can flow in one direction. Okay. Next. When current flows through a diode, a small positive voltage develops from the anode to the cathode. This is called the forward voltage drop. It's usually less than a volt. Voltage depends on the type of diode and the materials it's made from. The most common silicone type diodes, it is about 0.6 volts of a forward voltage drop. And that's just, it's an atomic level thing. It takes a certain amount of voltage pushing a certain amount of pressure before the current will start to flow. And like I said, it has to jump that 0.6 volt. Typically, there are diodes that called Schottky diodes that typically they're more like 0.3 volts, so half the voltage drop going across the Schottky diode compared to a standard silicone diode. And then there's other variations as well. So you it is variable. depending on the type of diode, but like they say, it's usually a volt or less. Light emitting diodes, or LEDs, give off light when current flows through it in the forward direction, going from the anode to the cathode. They're used as visual indicators. They use a lot less power than what the old standard incandescent light bulbs or lamps did. And they're a lot more reliable. They don't burn out near the same way that the old bulbs did. Material from which the LED is made determines the color of the light emitted. And back when they first appeared in my world, back in the early 70s, red was the only color you kind of like Model Ts only came in black. Well, LEDs only came in red. And as time has gone by, they've added more and more colors. And now you can get them in, white, blue, and the white's a pretty good white. So, and they have infrared. They've got all kinds of different variations of LEDs now. All right, next. Transistors. The function of a transistor is to control large signals with small ones. You can think of it as being an electronically controlled current valve. When used as an amplifier, a transistor produces gain. Transistors can also be used as a switch. You can design the circuit so that the transistor is either on or off with the signal change, and they don't operate in the middle mode. Okay? All right, we see electrical schematic for bipolar junction transistors, BJTs, and field effect transistors, FETs. The original transistors were the bipolar junction type. They use current coming in this symbol from the left, which would be the base, to control a current going from the top right to the lower right. And a small change in the base current causes a larger change in the current from the collector, which would be the top right, to the emitter, which would be the bottom right. So a small signal has a larger effect. On the field effect transistor, the incoming signal on the left would be that's called the gate, and then you had the drain and the source, which would be the top right and the lower right. It uses a voltage field, or the presence of a voltage will control the current flow in a field effect transistor. You have to have a current flow in a BJT. You only need a voltage present in an FET. All right. Common designator, when you see them on a schematic, is Q. It would be Q1, Q2, etc. Okay, two common types of transistors. We've discussed them. BJT, bipolar junction transistors, and field effect transistors. Two basic types. Bipolar junction transistor has 3 layers of N or P material that are connected to electrodes. Here we see the base, which would be the center of a sandwich, the collector and the emitter, which would be the outer 2 layers. Think of it as the bread in the sandwich. And they can be done in 2 different ways. You can have a PNP, in other words, positive on the outside layers and N-type material on the inside layer, or vice versa, NPN, which would have negative type material on the outside layers and a P-type material on the inside layer. 2 different variations on a bipolar junction transistor. And the way you tell them apart when you're looking at a schematic If it is a NPN, in other words, negative, positive type, negative type, then the arrow is not pointing in like what you have here. The arrow is pointing out towards the circle. That's an NPN, not pointing in. If it was a PNP type, the arrowhead would be pointing at the bar. It would be at the bar, pointing at the bar. Okay, so that's the two variations you have on a bipolar junction transistor. Next. Okay, so depending on the arrangement of layer, BJT is either an NPN or a PNP. 3 electrodes of a FET transistor are the gate, the drain, and the source. RF power transistors are used as the primary gain-producing component in RF power amps. The field effect transistor has a conducting path or channel of N and P material connected to the drain and the source electrodes. Voltage applied at the gate controls current through the channel. So it's the voltage present at the gate. That's what controls the current flow between the drain and the source. Okay, integrated circuits. Integrated circuit, call them ICs or chips, is made of many components connected together as a useful circuit and then packaged as a single component. So we take an entire circuit, condense it down to a very small size, put it onto a plastic or ceramic or whatever material die, and that is sold as a single component. And in this case, we have a IC down here. It's a 14-pin IC. Its type is a 7643. They got the number upside down, but you can still read it. It's made by Motorola. I can tell you that from the, you know what? That's a type 1400, 1400. I can't tell. That's the 60. That's the type. 7645 would be the production date. So it was made in the 45th week of 1976. But you have the whole circuit all in one little component. All right, so the schematic symbol, a couple variations. The square in the top with the leads going in on the left and out on the right. That would be a flip-flop, which is a type of circuit. But the component, the IC, is the whole circuit all in one package. And so it performs the functions of a circuit all in one component. The lower one, the triangle, that would be some form of what we call an op amp. And again, the entire circuit all in one little package. And sometimes they'll have multiple op amps in one package, and they are, you can use each one individually. There might be, 4 of them in one package. You would have 4 op amps available to use just by buying one little component. All right, next. The designator, when you see them on the schematic, is IC or U, and U is the more common one. Okay, practice questions. What is true about the forward voltage drop in a diode? The answer is A. It is lower in some diode types than in others. Like I said, it's standard silicone diode is 0.6. That's what most diodes are, but you do see some that are as low as 0.3 volt forward drop. Okay. What electronic component allows current to flow in only one direction? That would be a diode, answer C. Which of these components can be used as an electronic switch? And that would be a transistor. Answer C. Which of the following components can consist of 3 regions of semiconductor material? And that would be a transistor. B. What type of transistor has a gate, a drain, and a source? And that would be the field effect transistor. Answer B. How is the cathode lead of a semiconductor diode often marked on the package? Remember, there's 2 leads on a diode, the anode and the cathode. The current flows from the anode to the cathode, and we have a bar or a stripe on the diode to represent the cathode side. So answer is B with a stripe. What causes a light emitting diode, LED, to emit light? The correct answer is A, forward current. You hook it up in the correct direction for normal current flow in a diode, and it will emit light. What does the abbreviation FET stand for? That would be answer D, a field effect transistor. What are the names for the electrodes of a diode? Just discussed that a minute ago. That would be the anode and the cathode. Answer C. Which of the following can provide power gain? Transistors. Answer B. What is the term that describes a device's ability to amplify a signal? That word is gain. Answer A. What are the names of the electrodes of a bipolar junction transistor? And the answer is B, the emitter, the base, and the collector. Which of the following devices or circuits changes an alternating current into a varying direct current signal? Answer is B, a rectifier. And the most common of that is the diode. All right, which of the following is commonly used as a visual indicator? Anymore, it's the LEDs, light emitting diodes. Answer A. What is the name of a device that combines several semiconductors and other components into one package? The answer is C, that's an integrated circuit. Okay. What is the function of component 2 in figure T1? And the correct answer is C, it controls the flow of current.
And this is where we stop.
Yes, it is. So, okay, for anyone watching this, this is a re-recording. The original class, by mistake, did not get recorded. I didn't catch it. Howard didn't catch it. You know, that happens. So we took time, we sat down, and we re-recorded this lecture or discussion, or I can't call it discussion if there's nobody else talking, but this class, so that it would be available on the site for, you know, so it's not a missing class. So that's, but if you attended the class, and yes, it's different slightly because I expanded on stuff and I had questions from students and so on. So, but we wanted to not have a missing class, didn't want to have a hole in the course. So we sat down and we did the re-recording. So thank you for watching.